Welcome to How Debuggers Work. My name is Cy Brand. If any of this is interesting to you, piques your interest, I wrote the book, I guess, on How Debuggers Work. It's about 750 pages long, which is way longer than I anticipated, but if any of this is interesting, please do go check out my book. Now, what kind of debugger am I talking about? Today I'm talking about native code debuggers. We're writing C, we're writing C++, Swift, Rust, whatever. These are compiled languages, taking some source code, generating a binary, which we then run, and oh no, something went wrong, we want to debug it. We heard some examples earlier of people using GDB or Visual Studio CLI, and these are all different debuggers that you may be familiar with. These are the main points I'm going to cover today. First, we're going to look at kind of what does the architecture of your average debug scenario look like. And then we're just going to step through a bunch of different possibilities that you might want to do in a debugger and how they actually work under the hood, kind of demystify what's going on. If you have any questions during the talk, please just put your hand up whenever and I'll question, because we're covering a lot of different things here. So, our debug scenario architecture. These are the kind of main system components that we care about when we're debugging. Not all of them, this is a bit simplified, but we have, of course, our debugger. We have the process we are trying to debug, which consists broadly of the code that is running and the data on which it is operating. We have the binary that exists on our file system, which is kind of similar to the process, but some differences in the code that are important. We also in that bank have debug information, which we will learn more about as the talk goes on. Very importantly, we have our source code. We generally don't want to debug at the level of our process. We want to debug at the level of the high-level code we wrote in C or C++ rather than X64 assembly or whatever. Then, of course, we have our operating system. Note that there's no arrows going between these components. They're all up and down between the operating system, which then communicates with hardware. So, manipulating memory. Here, we care about the data it processed, and we are helped out by the operating system. This is through system calls. So a system call or syscall is a function provided by the operating system to allow user programs to perform privileged operations. And the main one that we care about is ptrace. Ptrace might look something like this. We can pass it ptrace peak data, says, hey, give us 64 bits of data at this address with this process identifier, and then a null pointer because ptrace is awful. Read memory, you send one command. If you want to do something else, you use a different enum, and then these other arguments change depending on which command you pass. It's a API design, hey. But this works. This will read memory from a process. There is, of course, security considerations, so you can only do this under certain circumstances, but this is kind of how it works. Some other supported operations are, well, reading and writing memory, but also registers, stepping over a single hardware instruction, continuing a process that was halted, maybe from a breakpoint, or attaching the process that's already running. Let's have a look at registers. Say we want to read the registers in our, say, X64 system. We might want to get all of these registers. This is something which Linux defines as part of ptrace, just a massive table of all of the registers in your system. And if we construct one of these and we give it to ptrace, hey, we get our registers. This is all just handled by the operating system for us. Maybe a bit simpler than you expected. breakpoints. This is one of the things that I think seem most magic about debuggers, right? Like you set a breakpoint on something and it halts. How does that actually work? Let's say we want to set a breakpoint on line 149 of petcat.c. There's two main things that we need to work out. The first is which machine instruction corresponds to that source line. Then, once I know that, how do I make the process stop when we reach that line? Well, the first part is done through debug information. So this is data generated by the compiler that maps your machine code back to the road. And on Linux, dwarf is the main debug format. Looking at our kind of architectural diagram that is here, from the code in the binary back to the source code. There then has to be some work done to turn this from a mapping from the process code back to the source code. I won't talk about a lot of detail because it gets a bit hairy, but just to be aware that this is some additional work that needs to be done. The mapping between the machine source code is done by the line information. This does exactly that, maps between lines of source code and addresses of machine instructions. And it's very complicated. It's essentially a table of information, but it's encoded as a custom bytecode, which your dwarf interpreter has to then interpret like it's a virtual machine. But it can kind of just look like this, right? We've got deep section, and the leftmost column is memory addresses of instructions. And in brackets, we've got the source code line and column that corresponds to. Kind of make sense? Seems not so good. So if we want machine instruction line 149 maps to, well, that's 0x1886. So we can set a breakpoint there. Good? All right, so we've done step one. We know to which machine instruction our source line corresponds. And now we need to know, how do we make the process stop? Well, there's a couple main ways to do it. We've got hardware breakpoints and software breakpoints. Hardware breakpoints are facilitated directly by the hardware. We have special registers that we write data into, and that does the breakpoints for us. Because with specific hardware registers, we only have a few of them. On X64, for example, we have exactly 4, which is not very many. But they are pretty powerful. They can break on not just executing, but also reading or writing an address. We'll focus on hardware breakpoints in a bit and look at software breakpoints for now. A software breakpoints, you actually modify the code that is running in your system on the fly in order to set a breakpoint. They're kind of theoretically unlimited, but they break on execute, not by reading or writing. So let's look at an example. Here we have some machine instructions in X64. These are the byte encodings. And here we have the assembly code. You don't need to read X64 assembly. Basically, that says move. It moves data. That says call. It calls a function. It's basically all you need to know. Say we want to set a breakpoint on the second move. What do? We actually go over here, take this byte, remember it, and replace it with a blank screen. Whoops. Not a blank screen. OXCC. OXCC is the instruction encoding for the int3 instruction, which is a specific kind of software interrupt. So software interrupt is something which will interrupt whatever code is currently running. The hardware will transfer control to an interrupt handler, which is registered by the operating system, and that will take some action depending on what the interrupt was. So your interrupts are usually just like a number, like 3, interrupt 3, which is the trap handler. So when the int3 instruction is executed, it's going to trigger an event. It's going to notify the operating system, which is then going to signal the process to stop. Now the debugger is watching. The debugger is waiting for this and is going to intercept that signal and say, oh, hey, this process is now stopped. I can go and report that to the user. Say, hey, we hit breakpoint. So to kind of walk through this, say execution is currently right here on the top line. We will execute that instruction, go to the next one, and stop. Now what happens when we want to try and continue, keep going? Well, actually this line, this purple line here is kind of wrong, because at this point, we're actually pointing at this 0x89, which is probably not a real X64 instruction. We've just gone over our XCC and we're now in garbage land. So if we execute this, we'll probably hit an illegal opcode. So what we do is, remember I took that byte and I remembered it somewhere. So I'm going to move the instruction pointer back. I'm going to replace the old contents, and now I have my move instruction back. So now maybe you think I just continued, but hey, what if this is in a loop? What if I want to hit that breakpoint again? Well, I step over the instruction, I put the breakpoint back, and then I continue. And then maybe I hit the breakpoint again, maybe I don't. Maybe the user asks me to disable it or delete it, whatever. But this is how it works. Any questions about software breakpoints? Yeah. The debugger is going to be, using the ptrace thing we saw earlier, it's going to be reading that memory, writing the bytes, and then continuing the process. Yeah. Yes, this is the instructions in memory of the debugging process, the process you're debugging. Does that answer the question?
How is the order modified in memory permission?
Good question. The question was about how does this, but usually when code is loaded by the operating system loader, it maps those pages as execute and read only. So because we're using ptrace, we get to do sneaky stuff that other people don't get to do. So we can write to the memory, that's fine. Any other questions? Cool. All right, Watchpoints. Watchpoints you're maybe less familiar with. How many people have used Watchpoints in here? Okay, a decent amount, but not too many. Watchpoints are great. If you ever had a memory corruption bug where you're like, this thing is getting written to somewhere, and I don't know where, use Watchpoints. Please, they're great. So I had this slide earlier, and note this bit here. Hardware breakpoints can break on reading, writing, or executing. So that's what we use. I mentioned that X64 has 4 debug registers. It looks kind of like this. We've got our 4 address registers, which can store addresses of places to set breakpoints. And then we have a control register. So say we want to set a breakpoint on address cafe, we would write that in there. Maybe we want to set one somewhere else. We write that in there. These are not currently enabled, because we haven't done anything with our control register yet. We're just getting set up. So the control register has these least significant bits are to enable these breakpoints. It's a little bit weird. There's 2 bits per register, and one of them doesn't make sense anymore because of how we've chosen to do operating systems. But yeah, 2 bits per register. Then we have just unused 8 bits in here, and then we have size and condition bits. I'm not going to go through exactly what the encodings of these are because it's not really important, but basically you get 2 bits for the condition, 2 bits for the size for each of the 4 registers. So say we want to enable the cafe breakpoint, we would write 1 into the least significant bit here. We'd write maybe a 1 into our condition, which says read and write, and maybe a 1 into our size, which is watch the 4 bytes from this address. So any of the 4 bytes from cafe are written to or read from, then we get an interrupt and we hit a breakpoint. And also there's a status register, DR6, which when we hit a breakpoint, this will tell us, oh hey, we hit the breakpoint at DR0, the first one. It would be here if we hit the second breakpoint. I made all of these dots because this is all a bunch of garbage that we don't care about right now. All right, so we're about at this point of the talk. Any questions so far? Yeah, Victoria?
Feedback. Could you emulate Watchpoints on software by doing some sort of trampolining, like you wait until you're ready for something and then you...
So you might be moving a bit forward, I can't quite hear you.
So I was wondering, can you emulate Watchpoints in software by like waiting before you got to something, you jump to some other place and save it?
Can you emulate software, hardware breakpoints using software breakpoints? You could do some kind of like sampling or something where you like pick some epoch and every so often or something you check if that address is being written to. I don't think you could emulate reading from without doing a bunch of like cache nonsense, like trying to read from it and seeing how fast it is to read from it, and maybe you can do like a side channel attack or something. I know that's just off the cuff, so I don't know if that's possible, but it seems maybe. Cool. So now I'm going to step on to stepping. There's a few different types of stepping at the machine instruction level and at the source level. With the source level, the ones we mostly use are stepping into function calls. So if we call a function, we want to go inside it. Stepping over function calls, so just skipping over the execution, and stepping out, going back to my caller. Instruction level step, as I alluded to earlier, is a simple ptrace call. Ptrace single step, steps over an instruction. Great. Step out, a little more complicated. We want to do something like find the return address of the current function through methods, which I'll talk about in a bit. And then we could maybe set a breakpoint there and just continue. So debuggers are actually setting breakpoints all the time, even if you're not asking for it, if you're doing some kinds of stepping, if you're doing shared libraries, as we'll talk about later. So they're often having internal breakpoints, which are just used to facilitate the implementation of other debugging constructs. Stepping in, a little bit more complicated. There's a number of different ways you can implement this, and different debuggers do it differently. Some of them would look for possible branch targets and set breakpoints on those, but you can think of it like working out which source line you're at, and then just looping step over instruction until you find that you're at a different source line than you started at. Kind of makes sense. You just keep going until you're at a new line of code. Yeah. Stepping over is kind of the same thing, but you can actually do some kind of disassembling of the function by trying to work out if the instruction that you're currently at is a call instruction, and if it is, then working out, okay, where's the instruction after that? Then setting a breakpoint on that and continuing. So you can kind of jump over this entire function call. And otherwise, we're just gonna keep stepping. This is heavily simplified. This becomes incredibly complicated as soon as you have things like tail calls, because they're just gonna jump and suddenly you haven't added a new function to your stack, but you're not having a call instruction. Or if you have inlining, it makes it even more difficult. So it's simplified, but this is kind of the gist of it. Stack unwinding. I hate stack unwinding, oh my god. Like, I thought when I was writing my book, like, I've written some basic stack unwinding stuff before. It can't be that hard. It's so bad. It's so bad. Okay, stack unwinding. So imagine that we've got a couple of functions, like find prey and nap, which I just stubbed out for now. Maybe we have a hunt function, which tries to find some prey, and if we find it, we chase it, and then we have nap. Naps are good. Have naps. Then maybe we implement a main function, which creates a cat called Pop-Tart, and says, hey, Pop-Tart, go on a hunt. Now, say we set a breakpoint, and we're inside find prey, and we've hit it. We might want to find how we got there. What sequence of function calls led to this point? And that's called the backtrace, which might look something like this. We have our find prey function, which was called by hunt, which was called by main, which was called by this start thing, which is kind of an implementation detail. But that's not all that stack unwinding is, because we could just as easily be in our nap function, and maybe we find, oh, there's a bug here whenever prey is empty. Maybe that's causing some data corruption. I don't know. But we want to say, hey, we're stopped at this point in nap, and we want to say, hey, debugger, I'm not actually at the frame above. We're actually here. Can you tell us the value of prey at this point? And this is a pretty common thing that we do in debuggers, like step to a higher frame. There's no actual stepping involved. There's no change in the state of the program. We're just saying, hey, debugger, imagine what would the value be here? And maybe prey is stored in some register, so we need to work out, oh, where was that register saved when the function was called? There's potentially non-trivial amount of work we need. So how does it work? Say we have our 4 frames here. On the stack, this looks kind of like this. We've got a stack frame for the start function, and then one for main, and one for hunt and nap. But what's actually in these? I don't want to go in too many details about stack layouts, but kind of generally speaking, the one right at the bottom would just be local variables, because it's not called any other functions. And higher up functions would have also the return address and any saved registers. And this would also be true for main and start, but I'm kind of running out of space here. So how do we work out how to restore these registers and work out where this return address is and the return address of that stack frame? Where we pretty much just have maybe a stack pointer, which points to the top of the stack. We might have a frame pointer, depending on how your compiler is configured. It may keep track of the frame base, it might not. If it does, it will probably stick it on the stack, and you can kind of walk up the stack that way, but it's still difficult to work out, like, which registers these are and how do we restore them. So we have call frame information. Now, call frame information, you know I said line table information is complicated. Call frame information is awful. It is a Turing-complete language. I wrote a programming language interpreter inside call frame information. It's that bad. So when I tell you this is very simplified, you can believe me. But it's basically a table, basically. Basically a table that has entries for, say, our program counter values down here, and it tells you how to restore different registers. This canonical frame address thing is basically just a base address for the rest of the computations. It doesn't really mean anything in itself. So our call frame information might say, oh hey, if the program counter is at this value, then the canonical frame address is 8 bytes above the current stack pointer. And if you want to get the old instruction pointer, i.e. the return address, that's 8 bytes above the canonical frame address. And the base pointer is unchanged. Then it might say, okay, but now if you're at the next instruction, the canonical frame address is actually different, and the return address is in the same place, but now we have an RBP. Can anyone work out, based on this, what instruction this is? Be very common in the prologue for any compiled function. So this instruction would push the frame pointer to the stack, because now the stack is now larger, the canonical frame address is moved by 8 bytes compared to the stack pointer, and the old frame pointer is now being stored somewhere. So you can kind of work out things about instructions just based on call frame information, which is kind of cool. And the rest would continue kind of like this. So it's basically just a big table of how to restore registers. And based on that, we can take our stack and we can say, oh hey, what would it be like if we went up here? And then we can do the process again and again and get all the way back to the top. Stack unwinding, it's great. Any questions about that before we move to something slick? Fine. Cool. Reading a variable. So I want to visualize the variable milkshake, the cat. I might have a cat type, which has a name. It has a floopiness and it has an age. And I might have my cat, milkshake, with the name milkshake, and a floopiness of 10 and age of 3. Now, at the level of the data in the running process, this just kind of looks like this. It's a bunch of bytes. Maybe if you look at it, you can kind of tell this bit is a pointer to the string milkshake. And you can kind of work out that that's a blank screen because I pressed the wrong button. But that one is OXA, or 10, which is the fluffiness, and then 3 is the age. So you can kind of work it out if you look at it. But that's based on our knowledge of how the structure is laid out. Wrong one, this one. We know how this is laid out, so we can kind of interpret those bytes. But we have to do that in a program. So we want to answer 2 questions. Where does the object live? And how should we visualize it? How should we interpret the bytes there? In our architecture diagram, again, we're looking at the debug information. So I'm going to show you some dwarf information. This is a textual dump of dwarf information, which is a binary format. This is produced from dwarf dump. And this is about type cat. We have this in bytes, and then we have its members. We have information about each member, what its name is, what its type is, where it is in an object of this type. So the name field is an offset, a byte offset of 0, and then byte offset of 8, and then 12. Make sense? Nice. Variables also have dwarf information. So we can say, hey, the variable with the name milkshake, that has a type. This OX61 would point to that definition that we just saw. And it has a location. Location, again, is defined in a Turing-complete language. But here, I've chosen a very simple example. It says what address is. And based on that, our debugger can take these bytes and say, oh, I know how to interpret these. I know what struct layout is. I found them through the dwarf information, and based on the dwarf information, I can maybe print out something like this, which just gives us a nice textual representation of those bytes. Nice. Calling a function. Say we want to call the function cat feed. We might have a type called cat, and it might have a member function called feed, which takes a number of treats to feed the cat and maybe returns the leftovers so we can give it to another cat or eat it ourselves if we're a bit weird. But we might want to type in poptart.feed and give it a number and then have it return a value, print it out. Now, importantly, this function might have side effects. Like maybe now Pop-Tart has the status full and will not eat anymore. Maybe it has to now go for a nap, I don't know. But this could change the state of our running program. So we have to actually call this function inside the process that is. We can't just like compile a version and make a fake cat and then call it. We have to do this in the running process. So it's pretty simple. Step one, you just write a C++ compiler. Kind of like production debuggers, expression evaluation engines look basically like compilers. Like LLDB calls out to Clang to do parts of its expression evaluation, or at least it did several years ago. I know they've been working on new stuff there. But what if we want to do kind of a more basic version? We want to write an entire compiler. What can we look at? Well, we can look at the veritable Bible of binary, the System 5 application binary interface, which is going to tell us how to lay out all of our registers and stack to call without actually having to write an entire compiler. I mean, this is what compilers are doing, but we can kind of fudge this. We don't have to write any code out into the process. We can just tweak some registers and tweak the stack a bit and make it look like there's a call to a function. So looking again at some dwarf information, might have our cat type, which has a size of 1 byte, and it has a feed function. Note this weird linkage name thing. That is name mangling. So because C++ supports function overloading, where it can have the function with the same name but different arguments, we need some way to deduplicate these names at the binary level so that we can say which function is being called when we eventually have to link all our code together. So this actually does encode our return type and our argument types in the symbol name. But we can also get them from our formal parameters, which say we've got a cat pointer and an integer. Where did that cat pointer come from? Because we didn't write it here. There's no cat pointer in that definition. Well, you might see that it's also marked as artificial. This is the implicit object argument, or the cat, which is having the feed function called upon it. So that is at the binary level just passed in as a pointer. How do we know that? Well, because of the Itanium C++ ABI, which is a different document and has nothing to do with the Itanium architecture, or rather it did originally, but now everyone uses it, unless you're MSVC. And so this kind of tells us how C++ should be morphed into something which can work with general like C linkers and things like that. So what originally looks like this will actually end up looking like this. Make sense? So say we want to call pop-tart.feed with 12. What do we need to do? What's like the kind of minimal thing that we can do to get this? Oh, we need to parse it. This is where we have to kind of pick how much we're going to support. When I wrote an expression evaluation engine for my debugger, I picked a very, very simple subset of C++ that will work with this, but doesn't have to support the entire gargantuan set of available C++ programs. And then we're going to look up the feed function, work out where it is in memory, and we're going to find the address of the pop-tart variable. And you can see this is all using stuff we've talked about before, so the debugger is constantly implementing things and then using those things to support higher level operations. So this all like builds upon itself. We then set up the arguments in a way which I'm leaving very nebulous for now. Set the program counter to the address of the feed function, which we found there. And then print out the return value, and through again, currently nebulous reasons, and restore the old program state. So let's look at that. Set up arguments and print return value. I mentioned the System 5 application binary interface. That is going to tell us how to set up our registers in our stack to call this function. So for a fairly simple function which takes 2 integer arguments, where at the binary level a pointer is an integer for purposes of argument passing, then the Sys5 ABI says, hey, stick the first argument into the RDI register and the second one into RSI. Then once that's done, our arguments are set up and everything should just work. If we set our instruction pointer to the address of the function and continue, we need to find a way to stop the program then just running off the end of it. That's difficult. Can talk about it later if you want to come up to me. But if we call the function, then we end up with this. The ABI says that the return value is put in REX, and it also says that the function may clobber either of these, so it's just written garbage in here. If we needed that, hopefully we saved it somewhere. But based on that, we know where the return value is, and we can print it out. All worked. Okay, so we're now at our final topic, which is shared libraries. This for me was when I was kind of learning about all the different parts of the debugger. This is just really cool to me. I hope you'll find it interesting as well. So say we've got an executable like this, cat petter. It's got a function called petCat and a function called getCat. Now probably petCat, maybe has to get a cat first, so this is gonna call that, and all of our stack unwinding and things like that would just work. But how about if getCat is instead implemented in libcat.so? Can we set a breakpoint on getCat? If we have a breakpoint in getCat, will stack unwinding just work and know that we're in a shared library and then be able to unwind all the way through this What if this is called by another shared library and this is called? It can get very complicated. This is further complicated by probably what you're most used to with shared libraries is, you link against them. And you can kind of imagine how information about shared libraries is stored in the binary, so maybe we can parse that information and we can go and find all those libraries. But what if this is done at runtime? What if we just call dlopen to dynamically load this shared library? Maybe it's a plugin system. This kind of stuff is done all the time. Can we make breakpoints work? Can we make stack unwinding work for something like this? How do we get notified that a new library has been loaded? So there's this thing called the debug rendezvous structure, which is stored at a known location runtime in your program on Linux. So there's this thing called the dynamic section, which is loaded somewhere that you can get to, and you can parse that information and find this thing. So it's kind of a protocol. It's a communication protocol between the dynamic linker and the debugger. So it has a version, and then it has a link map. This is a description of all of the shared libraries that have been loaded by this process, the paths to them, and where they were loaded in memory. So if we did get this, we can walk this and determine what shared libraries we need to parse and find the debug info for. But how do we get notified when there's a new one? Well, there's a few other things that we don't care too much about right now. And then there's this magic thing, break. This is the debugger rendezvous function. Whenever the dynamic linker loads a new shared library, it's going to call a function that it stores a pointer to here. That function doesn't do anything. It's literally a stub. You could find it if you go look at the source for the GNU dynamic linker. But it's called whenever there's an update to the link map. That means we can put a breakpoint on it. So what we do is our debugger will set a breakpoint on the debugger rendezvous function. Again, internal breakpoints used for implementing higher level constructs. And whenever it's hit, then we know, oh hey, there's been some updates to the link map. We can go parse it. So we do that for every library in the link map. We're gonna find that file and parse its debug information, put it into some internal data structures, and then whenever we have a query for set a breakpoint on a function, we're not just going to check the debug info for our executable, we're also going to check the ones for all of the shared libraries that would be loaded. And with that, we've covered all of the topics I had for today. As I said, this is only a taster of essentially all of these, and there are many more features of debuggers that I don't have time to cover today. If you want more information, you can come talk to me after, or you can go read my book. It's kind of good, I think, I hope. And that is how debuggers work. Thank you very much. Any questions? Yeah?
Do you have no operating system? What changes in this case if you're using a debug probe with data or something like that?
So the question is if you're operating debuggers over JTAG or on a microcontroller, things like that. I don't have that experience with JTAG, but for a lot of embedded systems, what they have is they run a GDB remote server. It's like a debug stub, essentially. The idea is that A debug stub should be a very, very small wrapper around whatever operating system facilities are available, like ptrace. In reality, like I think LLDB's debug stub got to like megabytes at some point, which is not great if you're running on a very tiny embedded system. But the idea is that implements very, very low-level interfaces. So if you want to, say, set a breakpoint on an address, it wouldn't have any symbolic information, such as, you know, what address corresponds to the feed function. So you would do that in your host. That would parse the debug information for your library, your binary, whatever, would work out the address, and then it uses what's called the GDB remote protocol to send a command to the debug stub to say, hey, set a breakpoint on this address, which would then communicate back saying, hey, yeah, that's set. And whenever it hits a breakpoint, it's going to communicate asynchronously with the debugger, who's going to like have a thread that's just waiting for GDB remote address packets, and it's going to communicate that way. Does that make sense? Cool. Any other questions? Victoria?
So for inlining and optimizations, I'm guessing there is some metadata that tells you, hey, this instruction is very in line from this function. Is it like that? There's anything fancier for that? Yes.
Victoria's question was for things like inlining. He mentions that there's some information about what was inline, where it was inline. Exactly. Dwarf information has tags for inline functions, and it will tell you which function they were inlined from, the range of addresses that were inlined, and it supports nested inlining as well. So if you're debuggers actually have to do quite a lot of work, especially in cases like you have a function call as the first line of a function that is inlined, and the first call to that function is also inlined. So you've got like one address which actually kind of belongs to 2, 3, 4 functions, however many were inlined right at the top there. So the debugger has to kind of recognize that scenario and then pretend that, oh, if you step in at this point, we're going to report that actually you're in the next nested function, even though you're still at the same address. So there's a lot of additional work that debuggers need to do to support inlining. It becomes very hairy. But yes, your intuition is correct. Victor?
So in languages that would allow you to have some sort of debug traits, where you would provide a special function that would format a particular data for debugging purposes, how would that fit in the expression evaluator to execute code that might not even be debugging? Let's say that code might be just for debugging purposes. It might not be like functional code that ends up in the debugging itself. So how would you handle injecting that code in the debugging process?
Cool. So the question is, reading between the lines a little bit here, you're talking about like, say in Rust, where you have like a debug trait which says, hey, for this, so Rust has traits for this print something as a string, basically, and also here's how to visualize it in a kind of debug manner. And Victor's question is about how could you kind of leverage that in an expression evaluation to use a debug trait implementation to print out a visualization with the potential complication that maybe that code is not even compiled into the final executable. In the basic case where it is compiled into the executable, I have no knowledge about how Rust trait implementations are mangled or anything like that, but what I would imagine is you know what the name mangling of these symbols are, so you can say, hey, I know where I can find, I know what the symbol is for the debug implementation for this type. I can go look up in my debug information or my symbol tables even, just in the object file to find the address of that function. And if it exists, then I could call it, and I know what the ABI is, so I know how to call it, and I know how to get the return value, which is just a string, I think. so you could use it like that. In the case that you don't have the compiled implementation of that, with some additional toolchain magic, you could try to find it, JIT compile it somewhere. You can, like debuggers will often just like map something into the memory of the process. So you could compile that function and map it into the running process and then jump to it. I think that would work. Whether tools do that today, I don't know. Can you tell me? You're just trying to pick my friend. Okay. Well, any other questions? Yeah.
How does breaking on throwing exceptions work?
Good question. Breaking on throwing exceptions. So, exception handling is again specified in the Itanium ABI. So there's a few runtime functions called things like _CXA new exception or something. I can't remember off the top of my head. But basically, you set breakpoints on those functions. So whenever the compiler is going to generate calls to those runtime functions whenever there's an exception thrown. So your debugger internally sets a breakpoint on those runtime functions, and then it knows the memory for the parameters and things like that. So it can say, oh, here's your exception type. I can do any of the regular stuff. Make sense? Cool. Yep. How do signals work? So signals are kind of the level down from the debugger, where it's a client of the operating system's signal handling features, where the operating system will have its internal representation of tasks, and depending on the operating system, you might have representations of tasks which are just for entire processes, or those might be individual threads, or whatever. There's a lot of different ways of implementing that. And then they will track what signals are pending for those tasks. And whenever you have to switch to a task, it will ensure that that signal is delivered, and any signal handlers that are registered for that signal are called, or in the case of something like a sig kill, it will just boof terminate process. So that's all handled by the operating system. The debugger just uses the operating system facilities like wait PID and to wait for signals. Make sense? Cool. Any other questions? I think we're pretty good. Yeah.
My subjective experience is that running an executable under the debugger on Windows using Visual Studio, the overhead there is very small compared to running on Linux under, for instance, GB. Of course, Visual Studio is proprietary and whatnot, but is there some extra or less magic that they do that GB doesn't, or vice versa?
So the question was that subjective opinion is that running an executable under the debugger for Visual Studio has less overhead than for something like GDB. By that, do you mean that, do you mean startup cost, or do you mean like running performance? So running performance for, and also are you talking about the difference between a release build and a debug build, or just a debug run bare versus a debug build run under the debugger? The latter one. Okay. So in the case where you have just a debug build and you're running it under the debugger, the slowdowns would be contributed to by things like parsing debug information, how good the caching for that is, any internal breakpoint stuff that is adding, any instrumentation that it's doing, which I believe under default running modes, GDB doesn't do any real like instrumentation or like runtime stuff. So off the top of my head, I'm not sure exactly what would contribute to GDB versus Visual Studio for runtime overhead, but those would be the kinds of things that would be influencing it, I would say. What do we have for time? Got time for probably 2 more questions, if anyone has any.
In some debuggers, you can jump back in time.
Ah.
How would you go about doing that for a native debugger?
If some debuggers allow you to go back in time, yes, they do. So time travel debuggers like UndoDB, Mozilla's RR, or WinDebug's time travel debugging, they work in quite different ways. There's a few different approaches that they take. You can do full emulation, where you just emulate the entire architecture, and then you can just replay it. You can jump to any point in that record, because you have control over the entire state of the machine software. That, of course, has very, very large overhead and is difficult to fully emulate multi-threaded programs as well. Some other approaches that are taken are snapshotting non-deterministic state. So most program execution is deterministic, right? You're just doing like move instructions or things like that. It's only things like IO, volatile accesses, syscalls, those kinds of things that are sources of non-determinism. So some systems will find those non-determinism points, instrument them, capture just the non-deterministic traces of your program, and then when you want to restore to a snapshot, it just goes to that point and then replays all the non-determinism in the same way. Any final question?
When you use the fork command in C or C++, it duplicates the process, so it ends up at...
Sorry, I'm struggling to hear you.
The fork command in C or C++, it duplicates the process, so it has to. Do the second one get attached, or has it just discarded?
Good question. So the question is, if you do fork, and in a Unix system, then that splits the process into 2. And the question was which one gets followed. It depends on your debugger and what configurations you use. So GDB has this thing called follow forks mode, which you can either set
Follow the parent
or the child. So GDB will instrument the syscalls essentially. Well, not instrument, will set breakpoints on the syscalls. Not the syscall themselves, the syscall shims in glibc. So whenever you call fork, then it will be notified of it, and it can decide whether to trace the child or the parent. You can do similar things for spawning new threads. Like whenever a program spawns a new thread, ptrace can notify the debugger, and the debugger can update its internal data structures to say, oh, now we've got a new thread, so we're going to have to take that into account when we get we're going to have to wait for more than just one process identifier, because on Linux, threads have different PIDs. Yeah, so that's kind of how multi-threading and multi-process stuff works. It's very much up to how the debugger implementer wants to implement that and what configuration options they want to give you. Cool. Well, that is us at time now. I will be around to answer questions today and tomorrow, and thank you very much for your time.